press this. Thank you so much, Rohan. Please go ahead.
Yeah. So I just want to introduce what we were working on in the ecs251 course for our project. So we read the Google Chubby paper, and we tried to implement some important bits and pieces that we were able to develop during this time frame. We'll go over the demo at the end. First, we'll talk about what was Chubby and what it is, what it was used for, and what it is being used for currently in the industry, and how it came about to be what it is right now. Then we'll go over the design of how Chubby is built and what different interactions happen when there's a server and the client, between the server and the client. Then we'll go over the implementation that we have done, because Chubby is a big, has a lot of modules to it. We were not able to implement all of them, but we were able to implement most of the important modules that we felt were more in align with the course that we were doing currently. So the RPC calls and some consensus protocols. So we were able to implement those. We'll go over that, like what have we implemented. And then at the end of it, Manas will be giving a demo of what we have built and how we built it and what exactly is going on in that.
Sounds good.
Okay, so first I'll introduce what Chubby is. So Chubby is a log service which is intended to be used within a loosely coupled distributed system consisting of a large number of machines that are connected by a high-speed network. It provides a coarse-grained locking mechanism and is very low volume for storage. It also provides an interface like a distributed file system that has advisory logs. So these logs are sustained over a period of time, and these are not hard locks, but for example, if one file is logged to one client and then another file, and that file gets client gets disconnected, and another client is able to get that log, so the server will still be processing the request by the client one before it switches its log to client two. So until and unless the client two doesn't start sending out requests, it will still be processing what client one was sending. In if it was a batch operation, let's say, so it will still be completing the request sent by client one. And once the client two starts sending its request, that's only when the Chubby cell will stop processing client's one request. So this is what we mean by advisory logs. The design emphasis for this algorithm was more for availability and reliability and not for very high performance or high throughput. And the Chubby algorithm for consensus uses Paxos in the paper. So the paper tells us that this Chubby was implemented with Paxos in mind, but we have not been, we were trying to implement Paxos, but we were not able to get a good library that had Paxos to integrate with our particular use case. So instead, we have implemented what is called a bully algorithm, which is a simpler consensus algorithm, but it does the job of a leader consensus algorithm. And then, so I'll go over the design. So in this, there's a Chubby cell, which has five master server replicas. So there's one master and 4 replicas in this. Then there are multiple clients which will interface with the master. And this client application will be having a Chubby library, which will be responsible for talking to the Chubby master in the cell. And this would be done using RPC calls. We'll go over what exactly we have implemented while doing RPC calls and what libraries we have been using. So that's for later. Right now, I just want to emphasize on the design overview. So in this, there is one replica server, 4 replica servers and 1 master server. These talk to each other using RPC calls as well. The Chubby cell, so this is known as a Chubby cell with the arrangement of 1 master and 4 replicas. So these run the consensus algorithm amongst themselves to elect a leader. And this is done usually by Paxos, but we have implemented using the bully algorithm. so the read and write requests are sent from the client to the master, and I'll just go over the read and write. So in the read and write request, what happens is the client sends out the request to master, and since this is a read request, this can be wholly satisfied by the master, so it does not need to contact replicas for the data of it, and it can respond directly. And when this is a write request, this master then talks to the replicas so that all the replicas have that data with them. And for writing, it first needs to acquire the lock. So that client first contacts the master to see if that lock, who has the lock currently. And if it doesn't have the lock, then it'll first acquire the lock and then start writing to that particular file or whatever that is. The file system that Chubby uses is similar to a Linux-based file system, and in where like it's the normal Linux-based file system that we have for our OS. And then in the bully algorithm, what happens is the client and the master talk to each other, and they send keep alives between them so that the master knows that the client server is alive, working, and it's still in contact with them. Overall, the master and replica send RPC calls to each other during the election phase, and then decide which replica is going to be the master. In the bully algorithm, what happens is the replica with the highest number, so replica number 5 has the highest number of like the number itself. So this is the 5th replica. So whichever replica has the highest number, that automatically wins the election phase and becomes the master. So in case replica 5 was supposed to get disconnected, so there would be no master in this, and then the bully algorithm would start the election phase again. And in this case, when we have 1, 2, 3, and 4 replicas, so replica 4 would then become the master. And this is how the election phase goes. So now, like, since now we know on a high level what Google Chubby is and how we have implemented it, so now I would like to let Manas go over the demo so that he can show exactly what we have been able to build.
Can you see my VS Code screen?
I think right now, is this still the screen from Rohan? Rohan, do you want to unshare your screen?
I'm trying to, I cannot actually find.
So there is an option. I think both of them are sharing the screen. So in view options, we can change the shared screen to
see.
Manas instead of Rohan.
Okay, let me see. How do I do that? I should look at view, you said.
Yeah, so there's a bar that says you are viewing Rohan Sood's screen, and next to that it says view options.
Okay, now for some reason I switched to, I think this is Manas' screen.
Yeah.
Okay.
Okay, so I'll go with the demo. So in our algorithm, like I'll just give an overview that we are implementing using we have currently 5 servers, and the dependence of them is such that like while we are creating the servers, like from the implementation perspective, we are making sure that first server 4 is up, then 3, then 2, then 1 and 0. Like there's some sort of a dependence between these servers while I've made the Docker file. While these clients have dependence on all these servers, now I'll just like I'll run this and I'll show what is happening over here. So if I do compose up, so first it will start all the particular servers, followed by the clients. Since we have some sort of a dependence, that's why we saw that server 4 was up, followed by server 3, 2, and 1 and 0. So maybe I can just pause this and I can probably just run this again and show the output in some other file. So let's say this is some result1 file. So in that file, we can just see what the outputs are. But the main overview is that first the servers will be initialized. By initializing, we'll say that first the DB is initialized, and then the bucket will be initialized. And later, there will be an election algorithm, which is the bully algorithm, happening between the servers. Since we have the server ID of server 4 as the highest, the bully algorithm works here, and server 4 becomes the master. And after that, we'll continue doing the election algorithm over a period of time. Uh, and I think we can stop this now, and we can go over the result. Mhm. Let's say we consider server 1, server 4 actually, which will turn out to be the primary, I mean the master server. So first the server is initialized, then we initialize the bucket for that, followed by that we say that okay, the server is running, and we initialize the RPC channel. The RPC channel is basically the way that we are doing communication between the servers, and then now like the servers will just ping each other, and now the server is starting the election. So now it will receive a message saying that all the nodes are initialized, and the master pings to the servers saying that what will happen over here is that the master will propagate the metadata between the servers, between the replica servers. As part of Chubby, what Chubby is doing is we are just replicating the metadata from the master to the server to the replica servers, and we can see that um, now I'll go through the election algorithm. So let's say this server, the server 4 receives a request that can I be coordinator from server 3, and I think that message will be 0, saying that okay, 4 says that no, that okay. So you can see that server 3 sends a request that can I be coordinator, and then the reply is no, that it can't be the coordinator because only the highest uh, node ID will become the coordinator as part of the bully algorithm. So this is the major part of election. And over here, we can see that the master pings to the servers that follow the master copy. So let's say the master has written some data to its particular database. Now we'll be sending that data to all the replica servers, and at the replica servers, this portion where we are sending data to the servers, replica servers, that is the propagation. And after that, we are just replacing, like that. How we have implemented this is like we are actually replacing the data which is currently at the replica server by the data which is being propagated. So, um, so master pings to the servers, follow the master copy, and check if master has a written DB. So if nothing's written at the DB, we are just going to say that we don't have nothing to send. Um, and and followed by, we can now move on to the client. So uh, let's say over here, now we can see that these white lines show that, okay, the client wants to read the file master. So all the read and write requests will be going to the master. For read requests, since it's an advisory lock, we're just going to need a shared lock, and as long as it doesn't cause any conflict, we're just going to read it. And if it's a write, if you want to do a write request, we'll just send it to the master, and then we'll require some sort of an exclusive lock. Though both of these locks are advisory. So client first requests that, okay, client wants to request the master. Then for that, we need the master IP, and this will be happening over here. And uh, I think other than this, yeah, we are actually sending keep alive messages over here. So in our implementation, keep alive is simply that we are just sending a message, and uh, it's just some sort of an acknowledgement that, okay, we send some sort of a message, some sort of payload, and we just get that message back. So this keep alive message is just like that. Uh, and other than this, uh, I think I don't think there's. I mean, this is just a standard, like the basic implementation of Chubby. So we've
Sure.
only done the basic operations for it. So by basic operations, we have keep alive, we have the client read request, we have the client write request. Then we have the propagation from the master to the server, the election process. We use this done through the Bully algorithm. Bully election algorithm, and uh, other than this,
Okay. Okay. Thank you. Thank you. May I ask you guys some question
Sure.
yes,
about
sure.
what you just done? So my first question, I noticed that in your demo, sometimes it's a client 4, sometimes it's client 3. They send a keep alive message to the master, right? So so I guess I just want to know a little bit detail is that I guess that the client sent a message to the master to make sure master is still alive. If the master is not alive, then they need to do the re-election, the leader re-election. They need to elect another master. So my question is that because all the client, they can actually, I look at 2 clients, I assume every client will do this kind of ping, keep alive message. I mean, how do we decide when is the time? What is the condition for triggering the leader re-election?
So,
Yeah, please go ahead. Please go ahead.
So
Sure.
the time where we go for leader re-election is basically when the clients on so the servers, they're talking to each other, and when the master stops getting requests and they're not the servers do not know that the current master, which is the highest node, it's not processing any requests. So that is when the re-election actually starts, that they get to know that they're not processing any requests and the RPC channel is not currently active and they're not sending any requests. So that is when the re-election starts.
So the re-election is really triggering by the server. Those
Yes.
server, not necessarily the client. So what will be the client's response if the keep alive message didn't go through?
So the client's response in the case would be, so basically in the paper, what the keep alive message is for. So ideally it is done. So what happens in the Chubby thing is that the client and the server have a session that is created. And during that time, the session is active. They keep sending keep alives to each other, sending that we currently have the lock, and the server knows that the client is actually there. And it's not just the lock is being actually used by the client. And if in case when it stops getting keep alive, the server knows that this client is not currently active. So it knows that it can actually switch the lock if it is being if any other clients wants to access that lock. So
that actually lead to my more a basic question, because simply is because I'm unfamiliar with Chubby, as you can tell. I'm going to ask this question. So we have a bunch of clients. How does the client know which how does client know which one is a master? Does the client, I guess another question is, does any client know every single server's address?
So for our implementation, what we have done is we have every client knows of all the servers, and they know that this they don't know of the master, but they do know that these are all the servers. And when they contact the server, that is when they know that this is the master. So that is when that is how they get to know of the master exactly in our implementation.
So initially they need to kind of like because I think this 5 server need to be, sorry, five different machine, and somehow we have to configure the service and such that they will know this 5 address, right?
Yes,
Somehow.
yeah.
Okay.
Yeah,
Okay.
so the client should know at least one server basically, so that
Okay.
the server can then
Yeah.
rewrite to the master.
Okay. And then from that server, they will be able to know the rest, right?
Yeah.
Yes.
Okay.
Yeah, so in the implementation, whenever we're able to establish contact with a particular server, so like the channel is established, and through that RPC channel, we are basically doing an RPC call to get the coordinator.
Right. Okay. So my second question is that you talk about the consensus algorithm,
Yeah.
and you said that you didn't use best source, but you use Boolean, right, to do your implementation. So I just want to confirm about the term, about when you set consensus algorithm, is the consensus algorithm like a majority vote type of consensus algorithm, or the consensus algorithm is Byzantine fault tolerant consensus algorithm?
No, it's not a Byzantine fault.
It's not Byzantine. Okay.
Mm.
All right.
It's a
So
majority word.
okay,
So
okay,
just-
okay. That's good. That's good, because Byzantine, then that's kind of more complicated, because what I'm worried is that the way you decide who is a master is who has the highest number.
Yes.
If I want to attack your protocol, then I would just make myself the identifier, the highest. So yeah, okay, all right,
Professor, I would also like to add something over here,
okay,
that in the paper, they are not considering any kind of Byzantine failures.
okay,
So, like in a particular Chubby cell, they just have included 5 replicas. And my assumption over here is that probably they are going ahead with 2f plus 1 failures. I mean, 2f plus 1 nodes, where f is the number of failures.
right. 2n
if,
plus
let's say,
1. Okay,
yeah. So if we need to account for Byzantine failures, probably like how we in a standard way we use 3f plus 1. So
right.
that is not being done in the paper. So it's accounting just for the standard failures.
Okay. Okay, that sounds good. Yeah, just for clarification. So earlier you mentioned the idea of advisory vote. I kind of get a little bit, but I kind of missed some of the explanation. Can you explain to me what's the difference between a regular vote and advisory vote? Remember, you use the term, right?
Yeah.
I think it is Rohan. You use the
Yeah,
term advisory vote.
Advisory locks, not
Oh, advisory log. Okay, okay, okay. I missed. So what is the difference between the regular vote and advisory log?
so
yeah. So
yeah,
yeah,
Miles,
please go
go
ahead.
ahead. Miles, go ahead.
Okay. Okay. So in an advisory log, so the conflict can only occur with attempts to acquire the same lock. So what I mean is that holding a lock isn't necessary to access the file nor prevents others from doing so. While in the case of a mandatory standard lock, we say that locked objects are inaccessible to clients which are not holding that particular lock.
Sorry, you say when the mandatory log is unavailable, then they can go to advisory log. Is that what you're saying?
No, so in the case of a mandatory lock, we like in case we don't have the lock, we cannot access the file.
I see.
So while in the case of advisory locks, the locks which Chubby service uses, uh, in this case, the conflicts will occur only with acquiring the same lock, just with acquiring the lock. What I mean is that a particular client can use can access the file without having the lock.
I
And
see.
no, it doesn't actually, yeah, it doesn't prevent the others from accessing the file. So it's sort of advisory that, okay, you actually need to have.
I miss the term. So you actually means advisory lock, right? Not law, right? It's LOCK, not LOG, right?
No, no, no.
It is advisory lock, right? LOCK.
LOCK. LOCK.
LOCK. Okay, I got it. Sorry about that. I misunderstood that part. Okay, so it's interesting that I'm trying to learning about the choppy. So my understanding based on your presentation, I haven't looked at the paper, is that any of the client, they can wait a minute. Let me actually check one thing before I ask the question.
So this is the link to the paper in case you're
Right.
interested
No,
in
I
reading
just
it.
take a look at the paper.
Yeah.
Yeah. So my question for this is that with the choppy, why or maybe how that it can prevent deadlocks situation? Is that possible to have a deadlock? And is that because of the advisory lock that you actually cannot have a deadlock? So I assume client want to provide a lock, right? Using the choppy. I assume you can acquire multiple lock.
Yes.
And if you acquire multiple lock, how do you actually make sure you don't have a deadlock?
As far like, if I don't think there's anything mentioned about deadlocks in the paper. So the use case of Chubby, I think this comes from the use case of Chubby, that if, since this is basically used for, this is actually a coarse grained lock. So by coarse grained lock, I mean that we are obtaining locks for a long duration. By long duration, I mean that, let's say it's for a day or two, so to, let's say, run a cron job or something. So I don't think there is any deadlock prevention mention in the paper, which stops from. Uh, yeah, there's nothing mentioned about deadlock prevention in the paper.
Yeah, I have to understand this a little bit more, but it's interesting. It basically provides a distributed locking
Yes. It's a
service
course.
that I think is a significant, is typically in any type of lock system, we have like a one single place that's actually coordinate all the activity. So that single place became a bottleneck for the whole locking environment. But with Choppy, that you have 4 or 5 different replica to actually allow you to do lock unlock in that scale. So there's a scalability over there.
Yes.
Yeah.
Yes.
Okay, I got it. Okay, that's good. I mean, it just whenever we talk about lock, is immediately we have to deal with 2 issues. One is the deadlock issue, and let me see the other one. So usually lock, we usually consider 2 property. Just technically, one is called deadlock. One is called mutual exclusion. We want to make sure that your lock, if it want to provide mutual exclusion, it makes sure that you won't allow multiple activity to enter the lock simultaneously. That's basically those 2 property. But you mentioned that this is the advisory lock. So advisory lock is probably weakening the second requirement. It's only, but still there is a concern about deadlock. I have to probably look at the paper more carefully. Okay, so let me ask you the other question. Have you guys done demo for number 2 and number 3?
No, we actually wanted to ask you if we could show that to you now.
Yeah, I don't want to
Uh,
show this right now because I
Uh-huh.
want to record this, but the TA is not here also to show you that. So I'm actually going to send a separate announcement, ask the TA to actually let you sign up to his doodle to do that. Okay, but if I need to do that very quick, so I can get your homework 2 and homework 3 grade as soon as possible. But let me turn off the recording right now.